G'day viewers. In this segment we'll talk about how signals propagate over wires and other kinds of media. This will take us one step closer to understanding how to send information across wires. Okay, here's the context. I think you've all heard me talk about this before many times. So on the left and right we have computers, which are really just sending bits. That's what we want, at least, from our links. But across the link they're sent as analog signals. We know that. We've talked about different kinds of media. Now, this means that we're going to need to represent bits as signals. To do a good job of that, we need to understand what happens to these signals as they propagate across media. That is our focus in this segment. Well, one of the first things we need to know is that signals in time can also be represented in a frequency space. Here's our signal over time. On the bottom left, you can see I'm just tracing over it here. Here's this signal. This is how we're used to thinking of a signal as going up and down and changing over time. Now, it turns out that that signal can be represented equivalently, so you can map back and forth, to a representation that describes the amplitude and also phase of different frequency components that are at harmonics. This first frequency component is a fundamental wave that oscillates maybe over the time period of the whole signal here. This second one, labeled 2, the second harmonic, means to add a component which oscillates twice as fast and with a higher amplitude. Then we're going to add another component which oscillates 3 times as fast with a smaller amplitude, and so forth. If we sum up all of these different oscillating frequencies, then, believe it or not, we'll get this equivalent signal on the left. This equation here, I'm just going to write OK to forget. I want to show you this equation. This equation sort of tells you how all of the different components of the frequency harmonics can be summed up to provide the original signal. But you don't need to remember the details of that. The important point for you is to remember that this mapping exists. This is actually a tool called Fourier analysis, which is widely used in electrical engineering. So any of you who are studying that subject, you can expect to get a lot more depth about our frequency space representations. The key issue for us is what happens to different frequencies as you send a signal across a media, like a wire. As you lower the bandwidth, there's a pronounced effect. As you lower the bandwidth, this means that fewer and fewer frequencies can get through, only the lower frequencies which oscillate less quickly. So you can see here in this box lost, I've taken the signal from before and I've scrubbed out all of the frequency components over 8 times the fundamental. This means that the components that I have left can only make transitions less rapidly. The effect is that our signal, which used to be this beautiful square signal that I'm drawing over here, has become more rounded. It's become this signal that we have left here. Why? Well, because when we threw away those higher frequency components, we lost a lot of the sharp corners. As you degrade further, as we lose more bandwidth, you can see that the signal here on the left becomes even more rounded. It's barely recognizable. And as you go down further, well, I can't even really make out that signal, whether it was a 1 or a 0. By the way, here's a question for you. Out of these 3 different channels which provide different amounts of bandwidth and effects on the signal, A, B, and C, which one do you think is good for data communications? Think for a moment. The answer is probably likely to be B is best. Why? Well, because we can usually make out whether the signal is a 0 or a 1. It's high here. 0, 0, 1, 1, 0. If those are the original values which were sent and we can recover them at the other end, then we've done a good job of using that bandwidth. We actually didn't need the higher fidelity signal. In a sense, we were wasting bandwidth. Now, of course, if you had an analog application like listening to a stereo, you want the high fidelity signal or it will sound terrible. Okay, so this last bit that we learned, that fewer frequencies degrade the signal by making it transition less rapidly and getting more rounded, is key to understanding what happens to signals as they pass over a wire. In fact, I can now tell you that there are roughly 4 rough effects here that happen as the signal propagates across a wire. First of all, it's delayed because it takes a little while for the signal to propagate, as we heard before, so a fraction of time will pass. Next, the signal is attenuated. Over a wire, a signal might go from meters through to kilometers. And the electrical signal that's going to come out the other side will be smaller in magnitude than what you put in, because some of it will be lost, some of the energy will be lost. The signal will also be attenuated or more rounded because not all frequencies will be passed through. A wire tends to pass frequencies well up until a cutoff frequency, and after that frequency the signals are fairly highly attenuated. They're mostly lost, as in our example. And finally, some noise is going to be added to the signal. Just thermal noise in the receiver, that's the sort of thing that you can't get around. And if the signal is very small, this noise will end up causing errors. I'm going to show you pictures of these effects in just a little while. We'll make them up. Before I do that, I just want to point out the information in the box here. Interestingly, the EE and the CS community have different ideas of what bandwidth actually is. In terms of the EE community, bandwidth is literally the width of the frequency band. So on a frequency diagram, some of the diagrams from before, we saw a range of frequencies. The width of frequencies a wire passes is its bandwidth. So it's measured in hertz. In the CS community, bandwidth is regarded as the information carrying capacity of a link. It's given in bits a second, megabits per second. We might talk of that as bandwidth. This is really, these two quantities are really related, because if you have more EE bandwidth, you'll be able to get a link which sends information more quickly. It will have more CS bandwidth, so they're certainly related, but they're not quite the same thing. So you need to be careful who you're talking to understand what they mean. Okay, so let's see those effects. Imagine that the signal on the left is sent. What's going to happen to it? Well, one of the first effects is that it will be delayed, but we're not going to picture that because I can't draw a time delay. Then it will be attenuated. What will that look like? Well, a smaller version of the signal will come out the other side. Now the bandwidth will be limited because we go through a wire and the high frequencies won't be passed. What will that do? That will make it more curved, so we'll get something that might look more like this. And then finally, we show here that noise is going to be added. What will that look like? Well, instead of being smooth, the signal may go something like this. It's still rounded, but it has all of these jaggies on maybe, because there's a little bit of noise. You can see here the amount of noise is small, so I can still see the signal very clearly. If the signal had been greatly attenuated, then the noise would be a larger component of it. So we've talked about wires. Now let's talk about fiber briefly. Actually, I have very little to add about how signals propagate over fiber. Most of the difference is to do with the physical characteristics of fiber. Now, in particular, this graph here shows you the attenuation of fiber versus frequency. It turns out that fiber has a very low attenuation, very low loss. And because of this, signals can go for miles and miles, up to maybe 100 kilometers through fiber, whereas they are usually greatly attenuated going anywhere near that distance through wire. Fiber also has these different bands here, shown in the red, green and blue, different portions of the frequency at which there is low attenuation. These windows are used for transmission of information because there's very low attenuation there. The scale on the bottom is wavelength. The wavelength is actually 1 on the frequency. And it turns out that each of these free frequency bands is very large. That means that fiber can pass large amounts of bandwidth, and that will in turn allow us to carry information at very high rates. This is why fiber can carry information at gigabits per second over fast links. Finally, we're going to talk about signals over wireless. Just as with wires, several effects happen with wireless. Now, first of all, like fiber actually, signals over wireless are transmitted on a carrier, not directly. Here is the signal that we would normally send over a wire. It's the same example from before. You can't send that out directly over wireless. Instead, what you do is modulate a carrier. So what I will do is I'll have a signal that's going up and down, and I will just change the envelope of the signal. So here the signal is going up and down very quickly. What I'm trying to do is draw, maybe I'm not doing a very good job of it, that the envelope of this signal should follow, this is actually the signal that we want to convey. Because it's an oscillating signal, it has to go up and down, which is why I have the component on the bottom. So I should almost be able to draw that. It should be a little cleaner. I'm not so good at drawing that maybe. A second effect is that these signals propagate. They travel at near the speed of light as they're going through air. They spread out, and as they spread out, they're attenuated. The energy has been spread over a greater volume. The attenuation is at least as fast as 1 on the distance squared. You might wonder why that is. Well, the surface area of a sphere is 4 pi r squared. So the energy has been spread out over an area like 1 on r squared. This, you don't need to understand too much of that. Just know that the attenuation is fairly rapid for wireless. This graph shows the signal strength versus distance. It's just a sort of a hypothetical for us to get the hang of it. You can see that as the signal goes out from A, its signal strength goes down like 1 on r squared. Now it's going down in both directions as you move away from A along the line a certain distance. The same is happening for a signal at B. It's going down at least as fast as 1 on d squared, where d is the distance from the transmission point. So this is the transmission point. And this is the 1 on d squared, where the d is the distance from the point of transmission. Another effect is that multiple signals on the same frequency interfere when they arrive at a particular receiver. So now I've drawn 3 signals here. What happens if we try and measure the signal like here? If we have a receiver that's fairly near C, I'll call that D. What does D see? D will actually see, what would you think? You're actually going to see this line at a particular distance crosses 3 different signals. We're going to see them all. So we're going to see, let's say, a strong grey, and a weak pink and blue. We'll see all of those signals. Now, of course, D won't be able to separate them easily. They will all be superimposed on one another. So really, it will see a mix of those colors if we're using a color analogy, which will make it very hard for it to understand what's going on. The notion of interference and the decay of the signal over time, though, does lead to the concept of spatial reuse. Spatial reuse says that you can use the same frequencies if you're far enough away because they won't interfere too much. For instance, if I want to receive signals over this region and this region, then it looks to me like A and B can reuse the same frequency. So we could have reuse here. So A and B, if we're having our receivers in this range, could transmit on the same frequency, because if I go down here, you can see within this region I only hear B, the signal from B, the blue signal, and in this region I only see the signal from A. The signal from B is just too weak to really be picked up. On the other hand, if I care about receivers in this middle region, between C and B, there's no reuse here. If you use the same frequency, then a receiver anywhere in that range would be receiving signal from C and B, and both signals would be strong enough that they would confuse one another. Okay, that's about all I'm going to tell you. Oh, actually, I'll tell you one more thing about wireless. I guess I want to say about wireless that there are other effects too. Wireless propagation is fairly complex, and it depends heavily on the environment, including how fast the sender is moving and where the sender is moving, what objects are around it, and what's happening at the receivers and whether they're moving. So it's a whole subject in and of itself. Fortunately, we won't need to know all those details. The other key thing to know about wireless is that the propagation effects, are heavily dependent on the frequencies you're using. RF emissions behave differently in the environment at different frequencies. Now, there's one key effect, the last thing I'll tell you about wireless, is an effect that happens in the microwave frequencies, and that effect is something called multipath. Multipath is important for us to understand because it has a big effect on communication systems. Multipath occurs because in the microwave band, signals bounce off objects. This means that they can take multiple paths between a sender and a receiver. On the left, here I have a transmitter, and on the right, I have receivers, TX and RX. Now let's just look at one receiver up at the top here. The signal from the transmitter is going to be sent out in all directions. Some of it might go directly to the receiver. Another bit of it might go in a different direction, but bounce off. A filing cabinet is the classic thing, and also arrive at the receiver. The receiver will then see two different signals that arrived over multiple paths. These signals will be superimposed, so they will add. Let's just say that we had one signal like this, and another signal which was also going up and down just as fast. When we add them, we get this strong signal. It's not faded. Now, suppose that just because of the position of the reflector, the path, the same thing's going to happen down at this other receiver. It's going to get a direct one-on-one via this reflector. But now say that the path from this other reflector has a different length. It will. And in this case, the phase of the signals is going to be a little different. So I'll receive one signal, just like this as before. And the other signal, oh gosh, how can I draw this? I'm going to offset. It's the same thing, it's just shifted. The result when you add these things together is that these signals mostly cancel, and you get a faded signal here. This is called multipath fading. The effect is very difficult to deal with because it can change over very small distances. As I move just maybe even a few centimeters, my signal might go from fine to mostly gone. This effect is also frequency dependent. The result is that in wireless channels, often you're in data communications, often your signal is really quite messed up. It's missing portions of it because some frequencies were lost. We then need to handle it with fairly sophisticated communication methods. If you're interested in learning more, you can look in your text. In particular, there's a method that you'll hear about quite a lot called OFDM that's used. We're not going to have time to go into OFDM in this course.